All right, so I'm just going to start talking so everyone in the hallway really knows it's time to come into the room. Not that bad. All right, so good morning, everyone. It's my absolute pleasure to welcome everyone to Annapolis. I'm glad everybody, some of you came from very far away to attend this workshop. And I'm truly, truly excited for the next couple of days. I firmly believe we're at the beginning of a new way of doing things, a new way of making measurements of our Earth and our nearest space environment for the future. And I'm really excited to have all the people participating and kind of setting the tone for how that's going to happen. So before I talk too long, it's my absolute pleasure and honor to welcome Matt Desch, the CEO of Iridium Communications, to give us a welcome and introduction. Matt?
Well, good morning, everyone. I guess, is that better to hear that? It's nice to be here, and it's really great to see what a great turnout we have today. Thank you to the National Science Foundation for hosting this. And as you know, this was an initiative started with Johns Hopkins APL and ourselves to exploit a very unique opportunity as we move into our next generation satellite system to be launched in several years from now. I thought I'd just take a few minutes, since there's a lot of discussion this morning about what the hosted payload opportunity will be and setting up sort of this opportunity before we get into the real meat of the days here with the science that's potentially able to be performed on next. To tell you just quickly about Iridium, what we are and what we're doing, and how this came about. I know many of you know of us. You probably followed this back in the 90s. I've been associated with this 5 years, but as you know, Iridium was launched in the early 90s by Motorola as a unique opportunity to create this communication sort of canopy around the world. It was an amazing technical achievement for its time. It was a very lousy business concept that they had, and obviously it failed from a business perspective as they raised billions of dollars during the dot-com boom to launch probably the most sophisticated commercial satellite system still to this day and still to be for many, many years to come. It was launched successfully in 1998. It went bankrupt in 2000, and that was going to be the end of Iridium. Of course, our predecessors, actually our company, bought Iridium in 2000. Probably thought we were crazy, paid pennies on the dollar for the system, but in turn, it is now one of the fastest growing, successful, high-tech communications company in the world. Some said, how can that be? Well, it's a little bit like building a luxury hotel. You don't want to be the first investor in it, you want to be the second investor in it. It's very difficult to make money at it. That's true of satellite systems in general because of the major capital expenses we go through to put a satellite system in the air. And that's why most of the successful satellite systems in the world, the ones you might have heard about like Intelsat and Inmarsat and Eutelsat, were basically owned by governments for the first 15 to 20 years of their existence. It's very difficult for a commercial satellite system to be successful. But about Iridium today, in the last 10 years, we've grown very fast. In fact, our compound annual growth rate has been in the 20 to 30%. Our bottom line in the last 5 years has grown at 25% or more. This last year, we just completed about $160 million of earnings on about $330 million of revenue. This year, we're forecasting another 15 to 20% growth on the bottom line. As a result of all that, I joined the company about 5 years ago and said, This company is growing very well. However, our satellite system, which by the way is quite healthy still, we have 66 operational satellites and 7 spares still in orbit. So it's quite healthy, but was only expected to last until about 2018, 2019. So we knew in the 2014 to 2015 timeframe we wanted to be replacing the system. Now, 5 years ago when I joined, that was an audacious goal that everyone thought was, unlikely, because with such a sophisticated satellite system as ours is quite expensive to replace too. In fact, we estimated on the order of $3 billion, and it's turned out to be about $3 billion is what it's going to cost us. Now, however, I knew growing as fast as we were, performing the important functions we do around the world. I mean, right now, we're saving lives, I think, in Japan, where we were the only system that worked when the tsunami rolled in. We are used on ships all over the world for cruise and for ships business. We're used in aviation, on aircraft all over the world. The only thing you can depend upon on a global system. Our machine-to-machine business, which are small, for asset tracking, monitoring, tracking, is exploding. So a lot of good reasons for continuing this service well into the future. So on that basis, we went and talked to investors, and in fact, have been successfully we went public about 1.5 years ago, so we're on NASDAQ, and then last year, in conjunction with developing our satellite system, we completed the financing of our system. Thanks to the French government, we have a fully financed plan right now, and we'll be launching our system starting the first quarter of 2015, and we'll complete all launches of 66 plus 6 spares, so 72 satellites plus 9 more ground spares, for a total of 81 satellites we'll be building. Are, as I said, fully financed, and we will be developing that, and that satellite system will take us all the way out to 2030 and beyond. So not a bad place from a company, given the auspicious background we started with back in the 90s. Quite successful company now, growing and fully financed for the future. Now, the history of the hosted payload opportunity, I guess, is quite interesting too. 4 or 5 years ago, as I said, when we were starting to plan for this and saw the $3 billion amount, we knew we would generate at least half of that ourselves, but we needed the rest, and we thought that one way to mitigate that would be to offer space on our satellites, on the nadir deck of our satellites, for hosted payloads. This is not a completely foreign concept in the satellite industry. Secondary payloads, hosted payloads, have been around for 40, 50 years from the beginning parts of space flight, but no one had ever offered 66 low Earth orbiting systems, all so close to the planet, all interconnected in space, all able to revisit every part of the planet simultaneously. That just doesn't exist, and by the way, probably will never exist again until we launch again in 2028 or something, or 2030. So we went out and started talking about, thinking that this was a way of mitigating the costs of our system. Now, fortunately, we've been offering that, and as you know, it takes a long time, particularly when you're asking governments to support financing and funding something to get deals done. And frankly, until we got fully financed, it was sort of hard to ask someone to sign up for it. But in the meantime, we've gone and gotten all the financing, so we really don't need to do secondary payloads or hosted payloads to complete our business plan and launch our system. So this is, if you will, this is the icing on our cake, if you will. But in the last couple years, as we got into this, we realized how important the things were that we were talking to, and what a good business opportunity it would be to have a hosted division, if you will, hosted payload capability on our system, and there has been a lot of interest, and so we've continued with it regardless of the fact that it's really not fundamental to our business plan. So we've been working this a couple years. This has been a very interesting opportunity. The GEOScan capability that has been created fits very nicely into our 50-kilogram payload allocation that we've made. This has been designed in. By the way, the hosted payload concept was an initial fundamental requirement of our system. So when we went out to industry and said, are you interested in building this, we had a lot of requirements for a hosted payload space, and it's been designed in, as you'll see, and we'll talk about that. Our prime contractor, Thales Alenia Space, is working this. I know some people here from our prime integrator that's working on behalf of that, Orbital Sciences. This is all part of our plan, and so it's a fundamental aspect. Now, I don't think we envisioned a couple years ago when we started this that satellites. We probably thought there would be one big payload and that would be it. Someone would use up all 50 kilograms. Being subdivided and put into space is actually quite interesting in some ways, and technically another just challenge that we'll overcome with having hub controllers and being able to manage multiple payloads at the same time. But fortunately, this is all happening quite early in the program, so it's all going to be accommodated with the system. So we're quite excited about the GEOScan opportunity. It fits very well. The size is great. The fact that it can accomplish some very, very important things to us, I can say from an Iridium perspective, is while it's a business opportunity for us, I will say it fits very well into our corporate culture. We've been very proud of what our system is able to do, the lives that we're saving around the world, the science, for example, that we've done even opportunistically with Ampere, which is probably one of the things that shined a light on this with us when we found out that our magnetometer could be used for global science, and I think we're only now appreciating just how powerful that worked out to be. The fact that we can expand that and do it in other ways is also even more exciting to us. There's a lot of corporate pride in knowing that we can do something like this. So it's a great opportunity. It fits very well. I think it's so great to see so many distinguished people here with so many good ideas of using this space. I applaud the efforts that you will be going through over the next day or two and the work that will go on. I think it will be exciting to see these missions launched and served for the next 15 years, which is one of the great opportunities, and I think it can do some powerful things. So I'm unfortunately not going to be able to stay for the whole day. If there's any questions or general questions up front that I can answer, I'd be glad to take a few right now about Iridium or about the overall opportunity, but I know that there'll be many things in the agenda which will cover it. Does anybody have any general questions you'd like to ask me now? I can understand this is still very early, so yes, back here.
Have you thought about giving people rides that want to be kicked off fly free?
We're not going to record this.
That's okay.
Have you thought about giving like CubeSat rides that can be then kicked off and fly free?
Yes. Have we thought about giving CubeSat rides and fly free? That was probably a consideration. It's a complexity we'd rather not deal with. One thing that I can say, you will see that, and maybe this will come out in this morning's presentation, is there's some discipline involved in being a commercial communication satellite system. We have to perform our primary mission first, which is to launch our system successfully, fly it for 15 years, and provide voice and data services to a growing number of customers around the world who will pay for that, and we will do that. And we will launch in the first quarter of 2015. I can't tell you how many discussions we've had with other payload customers who've wanted to expand what it is that the secondary payload capability will do and say, can you do 100 kilograms or 200 kilograms, at which point we're buying more rockets, we're launching, we're having a bigger platform, and probably launching 2 years later, and that just isn't going to happen. So that is both bad news in that limits the opportunity, but it's also good news, which means that we are going to get this thing done. We are going to launch in first quarter 2015, which means we will be on time, on schedule, on budget to make that happen. And that is the discipline of kind of working with a commercial satellite provider in something like this. Yes, down here.
What's the history of Iridium as element 77? Do you intend to have 77 satellites?
We're recording.
Yeah, so the question is, what's the history of the name Iridium with 77? And the answer, and it is interesting history in that it was originally envisioned as a 77 satellite constellation. As most of you know, we have 6 planes of 11 satellites. At one point, I think there were expected to be 7 planes of 11 satellites, but they realized very early in the program, probably in the early 90s, that if they raised the altitude just slightly, that 66 would work just as well. Unfortunately, as you know, that's dysprosium, which didn't make a very good corporate name, and so they decided to stay with Iridium. About the best marketing thing they did back in then. Yes.
I've heard mass volume and power allocations. What about data rate? How much bandwidth will be offered?
Yeah, and that will come out in the discussions this morning. There will be discussions. There is a bandwidth, a data rate possible. We actually have a lot. Our new satellites are quite a bit more powerful than the last satellites, which means also we're going to have much higher bandwidth in our crosslinks and in our downlinks. So we have more bandwidth to make available to a secondary payload, to a hosted payload, but I don't have the exact numbers. I mean, I think that'll all get covered in this morning.
Yeah, it's all going to be covered. So,
And nobody trusts me to give the answer anyway, so my engineering background is behind me at this point. So, other questions?
Yeah, with the satellites having to stay fixed up there with their designs, and then all the ground handheld smartphones and stuff expanding like crazy right now. Can you comment on what your strategy is for dealing with the handset or whatever you're going to call it in 10 or 15 years, and what that might do to leverage the satellites and make the service even better?
Yeah, thanks for the question. It's a good question. One of the unique aspects about the Iridium system, of course, compared to most satellite systems, is that we're not a bent pipe system. Bent pipe systems are all the intelligence is on the ground, and it's called bent pipe because as the satellite comes over, as long as it can see a ground station, the ground, it sort of just relays the signal down to a ground station. What's unique about our system is that all the processing goes on in the satellite, and it communicates with all the satellites nearby, the ones in front and behind it, and the ones, if you will, to the left and right of it. So it creates sort of a canopy of communication. So we use what are called crosslinks, and that means we don't care where the ground infrastructure is. We work just as well at the North Pole as we do at the equator, as any place else. Now, one of the benefits of that, I mean, there's one of the challenges of that is it's an expensive architecture, but we've solved that one because we're putting it through. But one of the powers is that it's so flexible on board, and in fact, the new next satellites are going to have a massive amounts more processing and memory power than our previous satellites did. Now, when Motorola built the system in the 90s, when they were still making satellites, they didn't envision the internet and the data rates and all those sorts of things that would happen. But as you can see, we're offering high-speed data today, and that was an upgrade really to our system to be able to offer more things. And the same thing's going to happen with these new satellites. We don't know what's going to happen in 2025, but we know our system is highly upgradable in the satellite system to be able to offer additional kinds of services and features. And then we do have control over the devices themselves, so we will see more and faster devices on the ground. Now, specifically, handheld is only one of our products. It's not the one most people recognize. It's not the big giant satellite phone as it was when it started. It's getting quite small. There's no reason, by the way, why we just can't take the chipsets out of that and put them into all kinds of devices for voice and data, so I don't really know where it's going to go. All I care about is that there's a voice and data link to it, whatever it might be, and we're going to see lots and lots of different devices. But sort of implied in your question is, when you said smartphones, is are we kind of competing against the cell phone guys? And the answer is absolutely not. If you want to talk about what the biggest business problem was back in the 90s, it was that Motorola created a system, if you will, to compete against cell phones. That was their concept, was that somehow you'd use this instead of a cell phone. We believe we learned the lesson very well, and we only complement cell phones because, I've used this a lot, even after 30 years now, it's been about 28 years since cellular was created, it still only covers about 7 to 8% of the Earth's surface. Our view is there's plenty of business in the other 93%, that we don't have to compete with that 7%. And if anything, we just complement it. So I expect that there'll be a lot more suppliers of devices, and we license our technology to lots of people who will build us in as a backup, if you will, or an alternative to terrestrial technologies, but then we'll work alternatively, and that's been one of our keys to success. I'm probably gone way over, haven't I? Shall we move on? Yes, we should. There's plenty of time, I'm sure, and a lot of these questions will be answered. All I can say is have a great conference. I think this is going to be a very interesting few days for all of you, and I know we really look forward to participating with you and supporting you. Thank you.
All right, thank you very much. We really appreciate the welcome. All right, next up, we have a slight agenda change. For those of you who know Ann Darren, our wonderful managing executive of the Spacefront and APL, you're going to be sorely disappointed because we have standing in for her as Bob Erlandson, the head of our space research.
Ann's a wonderful person, so I will really give the science perspective. But thanks, Lars. I would like to welcome all of you on behalf of the Johns Hopkins Applied Physics Laboratory. And for those of you who don't know much about APL, I just wanted to say a few brief words. We are located primarily in Howard County, Maryland, in Laurel. And there's about 4,000 of us. We do have a small set of field sites located across the country, but by and large, we're here in Maryland. And as part of APL, about 20%, 25% of APL is comprised of our space department, our space sector work, about 700 people. And we do missions for all sorts of customers, most recently NASA. And a few things I wanted to highlight here. I have some pretty pictures here on the chart here that really talk about some of the scientific discoveries that we've been involved in. And that's what we're after at the end of the day at APL, is really enabling missions that meet the sponsor's goals and to really make exciting scientific discoveries. So I've highlighted a few things here. You can see cover pages of scientific journals where we have documented discoveries. A lot of these examples are results from space missions. I think the most important thing recently is in the middle top, the messenger photo. That's the images of the planet Mercury that were taken during the recent flybys. And if you paid attention, about a week and a half ago, we inserted the messenger spacecraft into orbit around Mercury. And today, perhaps tomorrow, we'll be getting back the first images of Mercury from during its orbital phase, and for the first time we'll be imaging the south pole of Mercury, and it's very exciting for all of the participants in that mission, and for all of us, because that's about new discovery and really finding out new things about the geology and processes associated with the planet Mercury. One thing to note, and I hope this theme comes true throughout this workshop and this potential project, is we don't do these projects alone. We do these with partnerships with industry. We do it in partnerships with our sponsors, and then we do this in partnership with the scientific community. And we have the example of Mercury. That is certainly true. We have a diverse scientific team. We have the contractor base that enables the mission, and so it's really a partnership. And I think that's what we really look forward to for GEOScan. It's a beautiful example of partnering with industry and leveraging that opportunity, and then also working with the scientific community, which we're going to hear from today, for some of the creative and innovative ideas. And part of the things when we think about these grand challenges are really scientific discoveries, is we really want to be able to share these with people. When the universities, we want to share these with your graduate students and your postdocs. And so as we discover things and learn things for the first time, that it's really doing it together and really sharing it across, everything from new young scientists to the established folks. I remembered at Mercury we had a big, the orbit insertion was broadcast on NASA TV. And one of the gentlemen that spoke, I believe I get his name. I hope I get his name correctly. Robert Strong, and he was involved in the Mariner mission to Mercury about 30 years ago, and it was his dream, of course, to get back to Mercury, and he was, interviewed during that. You could see the excitement of him actually being able to see again parts of that planet that have never been seen before. So it's both the more well-established scientists who've been around for a long time, getting the joy of discoveries, along with more I'm sure his younger students and staff that see the excitement of making these first-time discoveries. So I look forward to this workshop and thinking about what can be made possible through this opportunity. So welcome.
Thank you very much, Bob. All right, so I guess it's my turn. So first off, I'd like to welcome everyone here, and just say again, I probably can't say it enough times how excited I am for the next couple of days. I think we have a tremendously exciting opportunity that's laid out in front of us, and I'm looking forward to seeing how everything unfolds, and I'm really looking forward to all the scientific and engineering talks that you guys have all come here to present. So mostly what I'd like to do with my time is really introduce how this concept kind of came about, and what we think is the vision for how to make it happen and push it through. And I'll talk a little bit about what we hope to accomplish out of this workshop and what we need to do going forward to make this program successful. So having said that, I'll get going. So this is the GEOScan workshop. My name is Lars Deard, and I work at the Johns Hopkins Applied Physics Laboratory. All right, so I like to start off every single talk that I give by saying why. You guys are all sitting here and probably like to know why, so I think it's a worthwhile question to answer. So in order to do that, I think it's worthwhile to say, all right, as geoscientists, what is our job? And I think we really have a couple of jobs. The first is quite obvious. Our job is to understand how the Earth environment works. Near Earth space, the oceans, the air, and the solid Earth beneath them. Now, if our job is important, I think we have a duty to educate the next generation, not just so they appreciate and understand the wonderful world in which they live in, but because the things we do are critical to humankind and our prosperity and livelihood going forward. So if they are critical, it's important that the next generation knows how to take over this job from us. So we always have this twofold motivation. And that's the same motivation of the National Science Foundation, to both educate and make scientific discovery. All right, so like I said, the work we do matters. It's not just there's interesting things that we study, and they are truly fantastic and interesting. But the things we do matter for everyone here on Earth. And it's worthwhile just to remind everybody of the numerous challenges we're facing going forward. Global change is probably paramount in the things that we need to understand as geoscientists. Obviously, unfortunately, in the most recent past, the Japanese tsunami gave a perfect demonstration that the things we do are important. We have space weather. This picture demonstrates, and I was speaking to a fellow from the State Department who was extremely concerned. He was now appointed to advise the president on science issues. He was talking to me about how they have numerous plans. They spent millions of dollars analyzing and preparing for what happens if a terrorist took out part of our electrical subsystem. And he mentioned that, for example, there's enough food on Manhattan to feed everyone there for 72 hours, just 3 days. So they realized, all right, we need to make sure that food continues to flow, and we're going to have mass rioting in New York if someone were to cut the power and all the food were to spoil on the island. And so their current analyses assume that they will still have power, because a terrorist attack would only locally affect a region. They'll still have power at the food warehouses that are about 200 to 300 miles away. But what happens when a space storm wipes out an entire grid infrastructure like it did in the late 80s when Quebec Power went out? They don't have a plan for that. It's our job to advise them on how to study that, and lives depend on it. Hurricanes are we're all too clear, particularly with Katrina and in Haiti, how they can affect the populace. And volcanic ash clouds. This is a picture from the Icelandic volcano. This is an excellent example. Flights were canceled for weeks. I know because I was stuck in Europe for several days. And billions of dollars were lost because we really didn't know precisely where the ash cloud was or where the particulates were. And so they had to cancel flights completely unnecessarily because we as scientists could not tell them how big the particulates were and precisely where they were. And as a result, billions of dollars were lost, and millions of people were affected as this. And so I see these things as our job. And the question is, going forward, can we continue to meet these challenges? And if we can, how are we going to do it? And I think that's what should be driving us as we're sitting here today. We should be focusing on these challenges and how we as geoscientists can meet them, not just for discovery, but to meet what is required of us for the society. And I think everyone here, I believe I'm preaching to the choir, so I don't even have to necessarily get in detail. I think nearly everyone here believes that really transformative new understanding and new science and also education really requires taking a global view these days. I don't think anyone here, we've flown, as Bob pointed out, APL's been involved with a number of spacecraft to study both the Earth and the near space environment. And that's what many of us are involved in. I don't think any of us have ever limited our goals to just one spacecraft scientifically. It always comes down to money. So we can never afford to do more than one spacecraft. I think anyone in this room would agree that given the opportunity, we would like to fly as many spacecraft as possible. And if we're allowed, we'd like to have them evenly spaced all around the world to allow us to take this global view. So really, what we think we need to go forward and meet these challenges is really constellations of spacecraft. But as I said, the first criticism that comes at you when you ask for a constellation is, well, no, we can't afford it. It's too expensive. We don't have the money to fly a constellation of spacecraft. Figured out how to do your science with a few ground measurements and maybe one or at most two spacecraft. But I don't think spaceflight necessarily has to be expensive. And I think that's one of the things we're here to demonstrate as well. And hopefully have enough network bandwidth. I also like to point out that everything that's going on here is being streamed over the internet. So many of you probably know that, so don't watch it on the internet. You use up our bandwidth and people won't be able to stream it. But this is an example of, it's a dad who he and his 8-year-old and 6-year-old son set out to fly an HD camera to the edge of space so they can film the blackness of space. And a lot of people say, well, that's not doing new science. But it's just a dad and his kid out there able to make this film. And it's been viewed by millions and millions of people. So the education potential is clear. And you could also say, well, that's not doing new science. And I won't force you guys to watch this stop and go film, but I would encourage you all, when you go back to your hotel rooms or whenever you get a free chance, to look up on YouTube Space Balloon and see what millions of other people are seeing in terms of the excitement and the science that one can do by extremely low-cost space endeavors. So it's an excellent inspiration that access to space doesn't necessarily have to be expensive. And these were the kids that were involved in it. And if you look at this is the picture that was taken as the balloon was immediately rising up. And this tells us education and inspiration aren't necessarily expensive here. That kid's probably going to be the next director of NASA in 4 years. All right, so I think at least this project, this Brooklyn Space Balloon, acts as inspiration to all of us that, yeah, going to space doesn't necessarily have to be costly. If we need constellations of spacecraft, we have an opportunity to meet these challenges, meet nations and societies' needs at dramatically lower costs. And that's really one of the main things we're here to do, is to demonstrate how that's possible. And that's why, when I learned about the Iridium Next program, I was absolutely floored. I had all these things in mind. I knew as geoscientists we needed measurements from constellations of spacecraft. And so it was clear, it was automatically clear that this is truly a once-in-a-professional lifetime opportunity. And I know as I look around the room and I see a lot of gray hair, for some of us this is clearly more true than others. And so this is really our chance to act. Because this is what the current Iridium constellation and the Iridium Next constellation looks like. As a geoscientist, we're interested in making uniform, system-wide, and global measurements. You could not design a better spacecraft constellation for the kind of things that we want to do. Their business model puts them making measurements everywhere on the globe. And that's exactly what we're looking for as well. And so it's really, I think, an exciting opportunity, and like I say, a once-in-a-lifetime opportunity to be able to put sensors on board this. So then on top of that, when I heard that not only were they going to launch 66-plus equally spaced constellation of spacecraft, they had put it just out there, said, we're going to do this. We are going to fly a hosted payload base. So if you would like to put something on there, now's your opportunity. As Matt said, people have been doing hosted payloads essentially since the beginning of commercial space. But nobody had ever come out right off the bat and say, we are providing a hosted payload opportunity just because we think it's going to be such a value. Whether anyone comes or not, we're going to do it, we're going to put it in. Typically it's been, well, we're going up there, and if someone happens to talk to me over coffee, we can put together a business model to fly their instrument or their payload as well. No one has ever put it out like a commodity and actually said, we will deliver the data, we will fly our payload, we will give you the power, this is what it is, this is how much it costs. So this is the main hosted payload specification. We're going to hear a lot more about this later on today, so I won't take too much time, but 50 kilograms, 30 by 40 by 70 centimeters, data rates up to a megabit per second. I said, wow, geoscientists, we have got to get our instruments on board. Then I found out how much it would cost to get the entire hosted payload bay on all 66 spacecraft. I said, no, we can't possibly afford that. And so that's what really led me to the next thing that really got me going, is when they decided to divvy up this space into small commoditized portions, into 10% chunks, and to find that, and they named it something called sensor pod. When I found out how much that cost, and so we're going to hear a lot more about sensor pod, but everything that GEOScan revolves around is making one of these sensor pods, which takes up 10% of the hosted payload space. So now we're talking 5 kilograms, 20 by 20 by 14 centimeters, 5 and peaking out at 10 watts power, data rates of 10 to 100 kilobits per second, and field of view that are either in RAM direction of the spacecraft or nadir viewing. So this is everything we're here to do is, all right, we've got this box. In CubeSat speak, it's 5.5U. It's not that big, but it's about the size of a standard instrument that we're used to working with here on the ground, or maybe a desktop computer. You can fit a lot of things in that. When I think about everything that's inside my smartphone, there is a tremendous amount of measurement and electronic capability. We've got GPS on the phone. We've got a camera. And that all fits inside my pocket. This is a much larger area than that. So we have an opportunity to say, all right, we can do a lot of science with this if we can fit small instruments in that take low power, don't necessarily cost a lot. I think we can do a tremendous amount of things. And so this is really what we're here today. What we're here to do today and tomorrow and going forward is we've got this box that we can fly. I think we can afford it. I think we can convince our government that we need to do it. We got to figure out which are the most compelling sensors to stuff inside that. And so the program that you're going to hear about as I continue talking and as everyone gets up to talk about is really designed to try to make the most compelling proposal possible. And in order to make about 70 of these boxes with geoscience instrumentation and get it flowing on all these Iridium satellites. And so you're going to hear a lot more about it later, but I'll point it out now. We think we have an opportunity to do what we're calling system sensors, which is the same sensor on every single spacecraft. And then leave open some space available for what we call a hosted sensor. So the system sensors are the same on all spacecraft. The hosted sensors are a unique opportunity to fly onesies and twosies and try out brand new and exciting new things. Now again, there's criticisms. There's always criticisms for when you're trying to do something new. And I think if we really want to maximize our science, it's about putting multiple instrumentation on, and for a lot of reasons. But people say, no, I'm sorry, my scientific measurement has to be the size of a Volkswagen Beetle. You can't possibly do anything new, anything interesting with a box that's so small and so low power. That's not science, because you've seen how big my instrument makes, and by the way, they cost $100 million a piece just to build. So you can't do anything new with small instrumentation. And that's why I was thrilled to come to APL, where Brian Anderson had been pushing for 10 years to get the necessary funding and get the support of the community behind the Ampere project. The current Iridium constellation has magnetometers for avionics, for attitude control of their spacecraft. And Brian Anderson knew that, if I had global measurements of Earth's magnetic field, we could do movies and images of the currents that are associated with space weather and the aurora. We could actually look at movies of what's happening right now. We've never been able to do that before. We have single spacecraft, or maybe photographs of the aurora, but that's not the same as the base level electrical measurement that's going on, that actually we can do a lot more physics with in the images. And if I could get a hold of all those magnetometer samples, I could do brand new things. People in the scientific community hear that, but those magnetometers are avionics magnetometers. They're not scientific grade magnetometers. They're orders of magnitude worse resolution, and we need to do actual science. So don't waste your time. We see no reason to do this, even if you've got a global measurement of that. Took him 10 years, but he finally got it going. And for the first time, we can view movies of the electrical currents associated with space weather and the Earth's aurora with an asset that was already flying in space for a fraction, 1% of what it would have cost if you devised this mission from the beginning and asked, we need this measurement, let us build a mission to go do it. This cost 1% to provide scientists with a movie for what it looks like with the electrical currents. And I think it was a fantastic inspiration for what we can do going forward. And it really acts as the inspiration for how can we take the model that Ampere has provided, which is limited to really space weather people. Space physicists and space weather people are really excited about Ampere. But it's somewhat limited in its scope, and it's not extensible to a lot of geosciences. But with this hosted payload and the sensor pod opportunity, we really have the opportunity to extend this concept to thousands and tens of thousands of science and address issues not just including space weather, but that are broader and compelling as well. And that's really what the GEOScan program was designed to do. What sensors could we fly that would make the biggest impact on science and society, given the fact that we have this global constellation? And so we think that we can make a big impact even if we have smaller, lower cost, lower power sensors, because we're doing something brand new that's never been done before. We're making those measurements globally and simultaneously. And there's a tremendous number of scientific things we can attack for the very first time if we have that possibility. And so that's what GEOScan is all about, is to come up with the most compelling sensors in science, given this, I think, fantastic once-in-a-lifetime opportunity. So I'll try to get in some of the details. I'm not going to talk about any science or any engineering details, because we've got a number of really outstanding presentations over the next 2 days that are going to make, I think, great and compelling science and payload suggestions. So I'm just going to talk about kind of the program concept and how we can push this forward going into the future. So really our goal, when it comes down to it, everything has to get paid for. And we think the best way to get this paid for is to propose as what's called an MREFC facility to the National Science Foundation. These are big type projects that typically cost around $200 million. All right, so MREFC is a major research, equipment, and facilities construction. And these are, like I said, large programs and large projects that an entire scientific community utilizes the opportunity and data from. Things that are too big for one PI or one institution to be able to accomplish all on their own. And so it's when the community gets together and said, if we had access to a big asset like this, we would make breakthrough discoveries. We have examples like Alaska Research Boat, major upgrades to the South Pole Station in Antarctica, and HYPER. So these are all examples of MREFC projects. And what we see GEOScan as being simply the same as this. So with HYPER, National Science Foundation got off the ground a little bit. And with CubeSats, now they're heading into space. And so we think GEOScan is just another opportunity that fits exactly into what they do. So GEOScan is really, it's a facility, it's an NSF facility from space that can provide breakthrough revolutionary data to the entire geoscience community. And so in order to really make the most compelling proposal possible, GEOScan is really, it's a two-themed science program. And again, like I said, everything revolves around this box. We want to make 70 boxes and stuff them full of sensors and fly them on the Iridium NEXT constellation. So you can always think back to this box. What are we going to do with this box? We have this defined volume, this defined mass, and defined data. What is the most exciting thing we could do with that? And we think that breaks down into two themes. One theme is accomplished by what we're calling system sensors. Like I said, constellation-wide instruments, the same instrument on every single satellite, to do things that we've never been able to do before with a global view. These sensors should be collecting data that really make critical global observations. We think with the sensor technology that's available today, we could fit 2 to 3 sensors in there. And that's one of the things we're here to help decide, help narrow down what are those sensors. It's really, you can view it as a geoscience community facility. So we want data that's of a broad interest to everyone in geoscience. The Iridium NEXT development timeline is rapid. That's how commercial space works. And so it requires us securing community consensus on what these sensors ought to be quickly. And this is the first step in that. And really, if we do these system sensors, we do the same thing on every single box, we can do things in a brand new way. It allows, for the first time, I think, scientists to achieve dramatic cost savings by doing things at scale. It's not typically how we think. We think about making a single instrument that is better than any other instrument to measure a certain thing than before. We don't think about what if I could make 100 of these, I can make them really, really cheap because we could design an assembly line, et cetera. I think there's a quick aside. When the first Iridium constellation was being launched, Motorola wasn't really in the space business, so they were naive enough not to know how to do it the slow and expensive way. And so they essentially set up a Model T assembly line to build each spacecraft. And by the time they were done with it, each additional spacecraft cost only $5 million. So it was a tremendous feat. Like we heard, it ended up not being a good business model, but I don't think that's ever been repeated essentially in spacecraft history. This idea of if you're going to do a lot of the same thing, even in space, the costs go way down if you do it over and over again. And if we use system sensors and make everything the same on all these pods, we have an opportunity to achieve those cost savings as well. So you're not asking how much does it cost to build one instrument. The question is how much does it cost to design and build 100? And that number better be a lot cheaper than it is to build one. All right, so we think these system sensors can achieve the following goals. Really, take data and enable science to solve pressing Earth and space science questions like I talked about in the introduction. They ought to make critical science impact. You should think of, all right, if I had all these measurements, give me the nature covers, give me the science covers, the cover of USA Today. It ought to be brand new and exciting, never done before. We should be able to provide data for discoveries, critical discoveries in climate, atmosphere, oceans, space weather, geodesy, and system dynamics. All these things are available to us, and we should attack the most compelling ones. In NSF speak, they're always talking about intellectual merit, really the scientifically interesting things that you should be looking at, and broader impacts. The system sensors have obvious intellectual merit, making measurements we've never made before in a global view. But they also have a broader impact. It benefits us for society. Because it's not the main thrust of this program, but it's enabled. Because Iridium is a real-time communications network, whatever sensors we put up there, as we do with Ampere, the data is available essentially real-time. So if we have this global observing network that we're doing science with, the availability is for us to get that data in real time. So when there's a critical challenge, like the Iceland volcano or the Japanese tsunami, we've got data that's helpful for policymakers. It's going to be there for us. And I think that's a tremendous broader impact. The hosted sensors also have their own unique and intellectual merit and broader impacts as well. We think with the hosted sensors, we're really inspired by the CubeSat community. So we're talking about leaving a volume of space open on this pod in their own science. So we're talking instruments hosted. So each of the GEOScan pod would have available space. These would be individual investigator proposed. So we would enable NSF to start a program similar to the CubeSat program where they have a solicitation, say, build and deliver your sensor for the following cost to be integrated with the GEOScan pod. And we'll be launching these pods over the course of 2015 to 2017. That allows you to do independent science investigations. Like I said, it's structured via normal solicitation process. So this is an individual PI-driven sensor and individual PI-driven science. And it really leverages the community CubeSat experience on what you can do with approximately 1 U, 1 watt, and 1 kilogram of space. And there's a lot of stuff you can do. So it has its own unique goals with the hosted sensor program. It gives, I think, unlike the system sensor program, you have the opportunity to really reach out to a broad range of scientists and engineers and train them, similar to the CubeSat community has been doing for the last few years. If we have 66 GEOScan pods waiting for 66 sensors to go in, we're talking over 1,000 students that would potentially be involved with producing and delivering that sensor and doing the science with it. And everything is going to happen over the course of a few years. So you have the possibility for a graduate student to work on the sensor and actually work with the data before he graduates. That's almost unheard of when it comes to satellite stuff. We think unlike traditional standalone satellites, which have been tremendously successful in education, we think this opportunity alleviates risk. We've got a guaranteed launch. We've got guaranteed operations, and we've got guaranteed data delivery. It allows the PIs to focus on the sensor and the science they want to do instead of the spacecraft bus, et cetera. Because we're eliminating the spacecraft bus, I think we dramatically reduce the barriers to entry compared to having a university-built satellite. You got instrument without the avionics and out the overhead. So we think this would dramatically increase the community that's capable of participating in this. Much smaller schools and much smaller departments could participate in such a program where it would be prohibitive now to build their entire satellite. It makes an excellent opportunity for really novel, high return ideas, riskier things, because there isn't a huge program depending on their success. It's a great opportunity to try that crazy idea that could just really revolutionize the way we measure things. And also, because we have the system sensors, we have this global network where we're providing a scientific context for you to make your measurements. So we got a two-theme program designed to make maximum scientific and educational impact. And I think without a doubt, this is really a revolutionary opportunity to make not just global, but massively dense measurements and dense coverage of both space and Earth. And last but not least, we really have the opportunity to act as a pathfinder. I think a lot of people in this room already feel the same way, but working with commercial space is an opportunity to dramatically reduce costs to do the things we want to do. However, the government is not used to funding opportunities that work on a commercial timeline. We really have to come up with a demonstration for how to do it, and we think this is an outstanding place to start. All right, so what are we here to achieve? I'll get down to the basics of it. We don't have a lot of time. So we have to identify the system sensors we're going to propose. So as I've alluded to, we are constrained with size, power, volume, and mass. For the system sensors, we want to be thinking of sensors. If we want to pack a number of sensors in this box, this 5U box, I think the nominal numbers to keep in your head, now things could be bigger, slightly smaller, use slightly more power, but just the ballpark figures I think we want to shoot for to maximize this opportunity is sensors the system sensors ought to be about a watt, about a kilogram, about a U, and if you're making 70 of them or so, you got to get their manufacturing costs down to somewhere between $50,000 to $100,000 a piece. And I know that's possible for a lot of sensors. If we're picking the sensors, we have got to define precisely the system science that these measurements are going to enable. That's what we need to make a compelling proposal to the National Science Foundation. And really, this program is named GEOScan because I think, like I said, it's not just global. They're dense observations. With this kind of measurement capability, this gives us an opportunity to make the kind of leap that's made from going from a 2D X-ray image of the body to a CT scan. And we have new opportunities, not just to make 66 times 1 of a great measurement, but because it's global and dense, we can make measurements in brand new ways, like doing tomographic imaging and things like that. The system science, or the science that's enabled by the system sensors, it should be broadly applicable. And foremost, it should be feasible. There's no sense in building 100 of something that's not going to work. And so we want to pick sensors that have a track record of working. And so we've put these kind of templates up on the website, and hopefully you guys have all looked at it. These are the kind of ideas that should be driving us as we're going forward and trying to make these selections. And so we want to pick system sensors that work their way to the upper left portion of this graph. So on the horizontal axis, we have things on the left side that are universally compelling. When you hear about it, like, wow, that's a great idea. That science topic excites me, and everyone should be interested in it. And we have things that are moderately important. I do a lot of moderately important work in my own research. I'm willing to admit it. So it doesn't necessarily fit over the left-hand side. And I think we all have to be willing to, on occasion, take a step back. Like, yeah, what I do is cool. But it's of moderate importance to things that are extremely exciting and universally compelling. And I think we all know the difference between those two things. We want to look for proposing the things that are going to work our way over to this side. On the vertical axis, we've got really the feasibility. Down here would be something that's the size of a Volkswagen Beetle. So a lot of the measurement, so a Volkswagen Beetle would be down here on the low feasibility side. It doesn't fit in a 5U box. Let's not bother proposing it. If you can get it small, if you can get the power down, if you can get the data rate into something that fits, then it works its way up here. So if we can identify 2 to 3 sensors that fit nicely in this category, I think those ideas are what should be guiding us going forward, because those are what's going to make the most compelling proposal. On top of that, if a single sensor or a combination of system sensors can really provide data that is of broad interest to a number of communities, not just a single discipline, I think that's a huge benefit as well. It's not a requirement, but it's without a doubt a benefit. And we've put this on the website as well and use GPS just to fill in examples of how guide people's thoughts. Not because we want to guarantee GPS is one of the system sensors, but I do think it provides an easy example for something that does provide data that's interesting to a number of fields. So for example, Earth, GPS stands capability of providing precise orbit determination, which allow you to do geodesy. You can do climatology or atmosphere, weather, ionospheric research, and magnetospheric research, all from the same instrument. I think it's useful to look for sensors that can provide this, not just because it increases the community that's going to be excited about working with this data, but if it can make multiple measurements from multiple spheres shall we say, it can do more compelling research, because we all know the Earth and the near space environment operates as a system. So if we can have a single sensor that makes measurements across that system, that's going to produce more compelling science. But don't get me wrong, having more people backing this program because we're providing data that's useful to them is not something to be overlooked. All right, on the hosted sensor, the timeline is a little less critical because the launches are happening over a number of years. But for the hosted sensor, it's important that we really demonstrate that a community does exist that wants to do science with something that's about 1 watt, 1 kilogram, 1 U. And since they're only building one of them, I think we can afford a higher price tag. If you can deliver your sensor and have it integrated for about $500,000, we think we can propose that within the program and make it affordable. So we need to include examples of possible hosted sensors that NSF would likely receive in our report. Because if we are going to keep on our timeline, a solicitation for hosted sensors is going to have to come out in approximately less than 2 years. And so we need to demonstrate that if that solicitation is released, there are going to be people out there proposing to it. And I know without a doubt there's going to be a tremendous response to it, but we need to demonstrate that concretely in our workshop report. So everything we're doing here is feeding down into these two things. We need to deliver a workshop report. We need to identify the key participants, and people that are going to be key participants are going to get stuck doing some work. All right, so when do we have to do what we're going to do? And so I've put our timeline, and I've laid it somewhat ugly over the Iridium timeline, because this is what drives us. We have to work under the Iridium timeline. It doesn't make our life necessarily easy, but like I said, we've been given a revolutionary opportunity. So I think it's worthwhile to try to work under that timeline. And you notice the main Iridium things to notice are the first launch in 2015, and PDR about a year before that. So we've got to come up with a timeline that works in that. So we've got, right now, here we're at the GEOScan workshop in 2011. Within about a month or two from now, I would like to deliver to the NSF a workshop report relaying what was both presented here and what was concluded at our steering committee, which everyone is welcome to is invited to on Wednesday. So that's where we're really going to give out assignments for, all right, who's going to do what for this report? What were the most compelling system sensor examples we heard? The sensor examples won't be locked down, but we need to write a report for at least what was presented here. The next step is to come up with a conceptual design phase report. Now, this is something that, as actually described by NSF documentation, this is essentially the first concrete step in the MREFC proposal process. When we come to this report, which I would like to do a couple months after the workshop report is in, so each report kind of builds upon the last one. We need to have the system sensors and the system science nailed down a little bit more specifically and have concrete and well-written examples of what the hosted sensors would potentially look like. So these are so this is from the NSF documentation of what needs to be in the MRFC report. And there's a lot of things to note out. We have to start coming up with more concrete budgets. We have high-level budgets right now just to see if things are order of magnitude correct. But we need actually extremely realistic and well-thought-out budgets when it comes to this phase. There's a lot of things we don't have to do. Typically, these MRFC projects involve breaking ground somewhere. So there's site selection studies, environmental impact, and things like that. We don't have to do anything. This satellite constellation is happening. The interface for how the pods will go in are already defined. So much of what would take a long time to figure out and decide is already decided for us. We don't have to do that. Because one of the things that I don't like to see is the entire process typically takes several years. That's not good. That won't work for us. This is the one thing in the MRFC process that does not work for us. There's nowhere that doesn't say you can't do space with an MRFC. So there's no rule against doing that. Our main problem and our main hurdle to overcome is that typically from proposal to getting things off the ground takes several years. And we don't have that kind of time. We have 1 year. So our main thrust is going to have to be to get around that fact. But I think we can do it. I think there's no reason to believe that we should let that stand in our way. And so if we can move forward successfully, we could start begin design and building at 2012 sometime. And allowing us to, about 6 to 8 months prior to launch, deliver our first GEOScan pods to be integrated with the rest of the spacecraft. We can wait so long before launch because we have a predefined interface. We will tell Iridium and Orbital up front what we are delivering to them, and then we can deliver it at the last minute as long as it meets those specs. And that's one of the great opportunities we have with this kind of commoditization of the hosted payload. So we have a quick timeline. So I've yet to speak to anybody about this concept who said, wow, that sounds like an awful idea. You should stop working on it immediately. Pretty much universally, everyone gets excited about it because scientists, they pause for a second when you tell them about this opportunity of flying 66 sensors to make global measurements. Like, wow, that sounds great. And they sit there still for a little bit, and they're thinking about, well, what would I do? And almost without a doubt, they come back a couple of minutes later like, what we should do is we should do X. And then if you give them another day, they've made that idea even better. And so I think we have an outstanding opportunity that everyone standing in our way it takes several years to get these things off the ground. That's the thing that's gonna get in our way the most, and I think we all have to work together to overcome it. And one of the best ways to overcome it is to make the most compelling proposal possible to NSF and really have it be self-evident that this program is necessary, it's got to happen, we all want it, and we think we need it. So the timeline is without a doubt challenging, but feasible. But we've got plenty of examples in our history, particularly space history, for overcoming challenging timelines. So this is where we were, suborbital, in 1959. And 4 years later, we were doing moonwalks. All right, same timeline we're talking about here for GEOScan. So when people say 4 years, you can't possibly do anything in 4 years, it's not enough time. We know that's not true. 4 years after that, we were walking on the moon. So it isn't that 4 years isn't enough time to build something and get it up in space. We know that's simply not true. Now, however, there was a lot of technical achievements that had to take place in order to make this all happen in 4 years, and a lot of money was spent by our government to make it happen. We're not talking about a lot of money, but we don't need it because we're not doing something that is technologically brand new. All the technology we need to do this program exists. We just have to put it together to make the program happen. So we don't need to do anything new. The only thing we need to ask of our government is the same kind of goal-oriented bureaucracy that enabled this to happen. We don't have to ask for a tremendous expenditure. And luckily, we think one of the main reasons to push this forward now is not that the time is right, but also the political climate for doing this is positive, I think. That does help us. We have challenges, but at least the climate that exists is positive for this type of thing. This is the President's space policy from last summer, where he has specifically called out for essentially 2 points. So I believe these 2 points combined together say, do a GEOScan program. You look at the bottom one, it says improve space-based Earth and solar observation. Capabilities needed to conduct science, forecast terrestrial and near-Earth space weather, monitor climate and global change, manage natural resources, and support disaster recovery and response. That's the kind of things that we want to do. That's the kind of things we need to do. It's exactly what we want a constellation to do. Also, in the space policy says, essentially instructs the government agencies to work with the commercial sector to both lower costs and shorten timelines and strengthen the commercial space base. This is exactly what we're talking about, these two things together. And so we think when we have this proposal say, yes, we know it typically takes years to do these kind of programs, but by the way, if you want to do these type of things, this is what they look like. Let's do them. Let us demonstrate how it's done. All right, so if we can overcome these challenges, if we can make this happen, what's in it for science and society? Like I said, I think it's an outstanding pathfinder for these public-private partnerships for space science. It allows us to, we all know budgets are getting tighter and tighter. That's a reality. There's going to be no way around it. Concepts like this, of cooperating with the commercial space industry, allow us to say, yes, things we do matter. They're important. Let us achieve our scientific goals, even at a dramatic cost saving to the taxpayer. I think we can do it. And really, this is the first time. We have gorgeous pictures from all the NASA and European Space Agency spacecraft of all these critical Earth and space environment. And what rarely pointed out when we see wonderful pictures like this that are tremendously scientifically informative and educational is, this is not an instantaneous picture of what's happening right now. These pictures often took several days or several weeks or sometimes several months to put together. So for many of these parameters, these critical parameters that we need for understanding the science of what's happening with the Earth and the space environment, we've never had this global, instantaneous view. We've never had a movie of what's going on like I showed you with Ampere. This is a brand new possibility with, I think, tremendous potential, and we just have to let our imaginations run and think of what we can do. As I mentioned earlier, because Iridium is a communications network, the potential's there. I don't think it's covered under this program, but the potential is there for real-time data. And I think our sensors can make a tremendous, valuable impact to certain things like disaster recovery and prediction. I think we have an outstanding educational potential with a program like this, particularly with what's enabled with the hosted sensor idea and lowering those barriers to entry for space science and science from space. I don't think it's a stretch to say if we got this program off the ground with 50 hosted sensors and multiple institutions providing the system sensors, the data and the technology that we would be working with and providing would result in, I think without a doubt, hundreds of PhD theses. There would be so many new things that would be required to work with that data that comes from a global view. There'd be new engineering theses and new science theses and new mathematics theses for the best way to invert this or that when you have global measurement. So these opportunities just await us. I think we could have participation from approximately 50 universities, particularly with the hosted sensor program. And that, without a doubt, would be thousands of students participating. And think about this. Picture these real-time museum displays. We've all seen them. You often see them at NASA. Are these displays of what's going on with the Earth with a particular parameter? What's the CO2 concentration? What's the ice cover? Could you imagine if you walked in the National Science Foundation and had 3 of these globes sitting there at the entrance telling you this is what the ionosphere is doing right now. This is what the atmospheric temperature is at 10 kilometers. This is the water content of the entire globe right now. These critical parameters, we all need to do our science. Could you picture looking at a globe or at a museum display of these things right now? Can you imagine the educational impact of saying, I'd like to talk to you about hurricanes and weather. Oh, and there's one right now. I'd like to talk to you about space science and the ionosphere. Look at this big blob of plasma right now. And that would be a fantastic educational potential. And I look forward to the day when that happens. And so it brings me to the end of my talk. And so I think we have both an outstanding opportunity, one that I've never seen the likes of before. We have some challenges to face, but I think they're entirely overcomable. We can overcome them. And I think to try to motivate us, if everyone is excited and interested in pushing this forward, I think no one should ever underestimate the power of the right idea at the right time. And so I'm really excited for the next couple of years. And with that, thank you. So there's probably time for a couple of questions. Yes, Atia?
I'm interested in the size of your hosted the sensor pod. You mentioned the size. What you didn't mention is that just a size of real estate that can be distributed, or it all has to be packed together? And where can it be put?
It's all packed together in a single box. We have access to nadir and RAM facing directions. So if you have a sensor that needs to look forward or down, I think we can accommodate it.
I see.
And everything's going to the same box. So like I said, our whole goal is to find out what sensors to put in this box that's 20 by 20 by 14 centimeters.
Okay.
Do they include the spacecraft or attitude determination sensors and all? Spacecraft sensors for attitude determination, attitude control?
So we're going to hear a lot more details about the Iridium spacecraft, but we are going to be, if we do this, we are going to be given access to kind of the things we need to know, the attitude and things, and the location and things like that. Excuse me.
Oh.
I have a couple questions related to the first one is, are you not allowing experiments larger than the standard sensor pod? And related to that is, how many sensor pods are you planning to fly per Iridium?
All right, so that's an excellent question, because I think there's it's something that needs to be cleared up and is worthwhile. So the concept of GEOScan is one of these sensor pods on every single spacecraft. However, if we can get this program off the ground, we don't have a lot of time, we think it's an outstanding opportunity. If we are going to be constructing boxes that fit the Iridium interface standard with the necessary backplane electronics and the necessary bus, we could make additional ones, just like Motorola did for the original Iridium spacecrafts, at practically zero additional cost. And so if there are science ideas or measurement ideas and sponsors that we can identify to pay for them, we think we can form partnerships to use these GEOScan boxes and other sensor pods. So for GEOScan, no, all the sensors that we're talking about have to together fit in a single sensor pod, so which really limits our size and mass of the individual sensors. But if we are successful with this program, we're going to be making these GEOScan pods, and we're going to be doing so at an extremely low cost. And it's an opportunity to reuse millions of dollars of engineering to make other low-cost proposals to other segments of government. So I want to have conversations with people who have sensors that are bigger than we can do for GEOScan, but could still fit in a sensor pod.
Okay. Another question, not related to the first one, but what lifetime are you assuming, and particularly what radiation hardening parts are you assuming for this type mission?
It's probably not going to look anything like your standard NASA stuff. I think you can get away with less. I think nominal numbers. I don't have the exact radiation environment numbers that we're expecting with Iridium Next. We could be working on those going forward. But I think like if something can withstand 10, 20 kilorads over, we would expect it to last for years in this environment. What is it?
It's a couple kilorad per year with 100 mil shielding.
Okay, so yeah, make something that can stand 10, 15 kilorad, and we'll expect it to last the lifetime of this program.
And for the views, there's a couple different pictures of the sensor-hosted pod. One has a big rectangle that's kind of perpendicular to the RAM direction. One's in parallel with RAM direction. Does it matter, or is it set already, or is that still being defined?
I don't think it's set. I think the options are defined, but it'll be determined by what the total posted payload customers that they identify are. I think they'll orient the sensor pods necessary to accommodate everyone.
And my final question for now, anyway, is on the cost estimate. Are you assuming kind of data analysis in those numbers, or is that just to deliver an instrument?
Not really. That's I think that's for getting the data. So that's essentially just cost estimate. We took the standard size of a major research facility, say $200 million, and said, what can we do for it? And those are the rough order of numbers that come out of it. So when I say $500,000 for a hosted sensor, I think that's going to be up to us as a community in conversation with the National Science Foundation of what that $500,000 should cover. That's about how much one could afford for a $200 million program if you wanted to do 30 or 40 of these hosted sensors. So yeah, we'll have to figure out what that's going to include, what's feasible for that to include.
Could you speak to what the strategy will be about allocating telemetry bandwidth, and is there a plan to have some sort of dedicated onboard processing to minimize the use of that bandwidth?
Oh yeah, without a doubt. We're going to have processing on board. And I think that's one of the things that makes this lower cost. We can have a single processor serve all the sensors on the sensor pod. So we can typically, a sensor includes the necessary processing hardware and then the measurement device itself. And I think we have an opportunity to say, let's do all the processing in a central location at the back of the GEOScan pod, and then that way the sensors can just make their measurement. So I think that's the best and most cost-effective way to do it.
The notional sketches seem to suggest that there's a limited view to the sides. Is that not going to be available at the end?
Presumably there is. There should be some view to the side. I don't think people thought about. I think Chad's probably would be able to speak to this better. Perhaps cover it in your talk.
Yeah, I'll cover my talk.
All right. Any more questions?
I don't really understand your cost model. I estimated myself about $500 million in cost and that's a lot for NSF to absorb, given their current budgets. And that's data analysis students and constructing everything. And that has to be allocated over the next couple of years to get this program going. So are you thinking of looking at other agencies, NASA and NOAA, for example, as also possible partners, or is it just an NSF program?
Oh no, I think we should be definitely aggressively pursuing NASA and NOAA. The problem is there's a couple of challenges to doing so. This isn't the way NASA does business, and if we do it their way, we're talking about a $2 billion program at the minimum, and that's just not going to happen. NOAA's charge is operations, and so since this has never been done before, and many of the sensors we're proposing are to some extent experimental, I think it's difficult for them to pay for large portions up front. If we get those sensors up there, I think there will, without a doubt, be NOAA and NASA money available for doing analysis.
But once you get them up there, the program's already over. I mean, in the sense the launches are already locked in, and so you get up and you demonstrate and take, say, a year of data. By that time, you're already committed for your last few.
At least 5 years, with all Constellation up.
Well, I looked at your launch dates. You're 2015 to 20. what, 17?
Yep.
That's 2 years. So say that 2015 launches and you get the data for a year, 2016, it's too late to say, oh, we like this sensor, we're going to put more on it.
Oh, no, for the system sensors, those are all decided. We have to know by next year exactly which sensor we're putting and have the
so somebody
manufacturing
has to
plan
pay
in
for
place.
those and everything like that.
Yeah, that's the hosted sensors can do that staggered timeline. So the people that are coming with the first launches better be ready right away. They probably have the sensor sitting on their desk. Now there's an opportunity for the later launches, the hosted sensors, since we can deliver before launch. They have many years to plan and think of their new technology.
Or 2 years?
If the first solicitation comes out next year, the last launch solicitation would be perhaps 2 to 3 years prior to that.
I don't think you understood my comment. Once you launch in 2015 and you have even a hosted sensor and it gets data to convince NOAA to say, oh, this is a great sensor, it's too late to build more of them to make the decision. So you can't do it at that point. So that's what's confusing them to me a little bit. This compressed timeline and ability to convince like NOAA or another agency to do that. But I'm done.
No, I think that NOAA would probably be more interested in the system sensors, the sensors that were on all of them. They may be interested in some of the hosted sensors, but I think without a doubt our target would be for those system sensors. Jesper.
Okay, just one brief little question here from a foreigner about to return to his foreign country. So can you say a couple of words about foreign participation in all of this?
Yeah, I think we've got and really the MRFC program looks for and evaluates foreign participation. I think we have two really obvious ways of having foreign participation. One is in what I just said. If we're going to make these sensor pods, we can make more of them and help advise other individual countries who want to use just perhaps a single or two GEOScan sensor pods for their own sensor. The other thing is at least our rough cost analysis doesn't include all 66. There's not necessarily enough money for hosted sensors on all 66. There may be 20 that we don't have money to fill. There's a great opportunity for a single foreign partner to buy their way in with their own hosted sensor. It's their sensor. A small country can have their own space program and their own measurement. They would own the data. It would be all theirs. So there's two ways, with an individual hosted sensor and a GEOScan pod that aren't being used by NSF, or an entire GEOScan pod, taking advantage of the engineering that's already been done. I think those are two obvious ways for international collaboration and participation.
So I don't want to speak for Thales, as far be it for me to do that since I'm from Boeing, but your schedule makes me real nervous versus a PDR and a CDR. If I'm a prime integrating an unknown payload, and it is unknown no matter what you say about the spec, I'm really nervous. I don't think your schedule is quite as fast as it should be. I know that's going to be really hard, but you have to test to a specification, test to a mass balance. There's a lot of things that you can't guarantee with leaving those hosted payloads that far out.
Oh yeah. So as the integrator, what APL would have to do is to guarantee a certain specification that everything we deliver to you meets this, and we will ensure that it does. Yes, that's the only way we can do it.
It's a large, as part of sensor pod. As part of SensorPod, there is a test and verification process to verify environmental levels as well as interfaces before it actually shows up to the spacecraft. So there is some thought behind that.
So Bob just passed me a note earlier. I think since this is being broadcast on the web and being recorded, when people ask questions, if they could stand up and introduce who they are and where they come from, that would be great for when we're reviewing the tapes, or for people online who can't see, and for all of us who don't necessarily know everyone. Are there any more questions? Or it's very bright, so I can't see.
Tommy and JPL. Can you briefly give me sort of the one-sentence go-over as to what a sensor pod versus a system payload versus a hosted payload is, and if it's the idea that NSF would be supporting one sensor pod of potentially, I guess, 5 that are available per spacecraft?
I think how many are available is going to be up to what Iridium sells. But yeah, so the GEOScan concept is that NSF would support 10% of the hosted payload based on Iridium in the form of a sensor pod on each spacecraft. So one pod on every single spacecraft that they're launching. So within that, we've defined system sensors, which are the idea of, for a lot of reasons, we think we want to put the same sensor on all 66 spacecraft. So we can engineering is much cheaper if you do the same thing over and over and over again. But because the science and the educational potential is so great with being able to integrate a few unique sensors, we think the hosted sensor program is worth the extra engineering cost of being able to do unique sensors and open that up to a very broad community. So that's the hosted sensor, a unique, potentially unique sensor on one or two of these GEOScan pods. More questions? All right, we should probably keep going. We've got a lot of ground to cover. So up next is Om Gupta, who's going to talk in more detail about the sensor pod opportunity. You want to, is it that one? Okay. Pointer. Can everybody hear me all right? Yeah?
Good morning. My name is Om Gupta, and I'm Director for the Marketing and Business Development on Iridium, next program. In my talk this morning, and I'll try to keep it brief, because a lot of the material that I had thought of presenting has been covered by, starting with Matt and Lars, and you will see a lot of it coming up with Chad as well. So I'm just going to give you a historical perspective, and here you will find in one place all the information that you have heard up to this point.
Oh, I think that's fine, because we've heard it all a million times, but not everybody else has.
All right. Before I start, I just want to say that ever since we at Iridium came up with this concept of sensor pod, which is not very far long ago, about 6 to 8 months ago, we've been working with two great partners of ours. First one is the Space Dynamics Lab. You heard Chad in the back of the room, and we started with them initially, and then we expanded that to Johns Hopkins APL. And they have been a great and very enthusiastic and energetic partners with us, and they have done a lot of groundwork, which will help answer all the questions that we heard earlier about how we're going to integrate this, what is the specification, and you will see all the great work they have done to really make this a reality that we think is a great opportunity for this community. So you will hear more about it. Once again, we are a commercial company with the second largest provider of mobile voice and data services. I just want to point out that we have our open port device that gives you 128 kilobits per second, and our handset, and our little device here called short burst data modem, which gives you M2M capability. This is the view of a week of the traffic on our network. And you can clearly see the global nature of the traffic. You can see the three kinds of traffic, starting with M2M, which is the white dots. If the yellows were not there, it would be all white, pretty much, or North America and many other parts of the world. The voice calls, which are overlaid on top of that, and the purple are the 128 kilobits open port traffic, where you can see the C lanes and so on. And more importantly, this is the month of February, and you can see a lot of traffic down in South Pole, which is coming from lots of scientists in that part of the world. Just to give you a program update, contract has been awarded to Thales Alenia Space to build the next generation constellation. 81 satellites are to be constructed, 66 operational to replace our current constellation, 6 on-orbit spares and 9 ground spares. SpaceX Falcon 9 is the vehicle chosen for the primary launch, and they would have been contracted for 8 launches. First launch in 2015, and the last launch in the Q1 of 2017. As Matt had mentioned, we have secured the loan facility for $1.8 billion through COFAS, which is France's export credit agency. On the hosted payload, Thales has selected Orbital Sciences to do the satellite integration and as well as manage the hosted payload integration. Our schedule that you have seen a view of already really supports the hosted payload integration to the pretty much 9 months prior to the launch, and could be even less if everything is standardized. A couple of key dates to remember: the satellite PDR is Q1 of 2012, and anything that doesn't fit within our specification must be committed by then, means the contractual commitment by that time. If it does fit, you have a little bit more time until the CDR, which is the Q1 of 2013. Just to recap the top-level specification of our constellation and what we are doing, here's a picture of the satellite with the hosted payload box right at the ram edge and looking towards the nadir. It's a polar orbit, 780 kilometers altitude, 86.4 inclination, and gives you about 100.8 minutes of orbital period. The launch is from 2015 to 17, and we have multiple orbit spares, as I mentioned, and we also have backup Earth stations. So these 81 satellites would be completely compatible with the current constellation. To simplify, so complete backward compatibility, network transition and continuity would be seamless. Ground architecture is already being updated as we speak, and Iridium Next is really a very different satellite than from what we have today. It really doubles the capacity of our subscribers for our main communication mission, supports higher data speeds up to 1.5 megabits per second on the L band and possibility of 8 megabits per second on the Ka band. Software upgradability that Matt had mentioned is a key feature which allows you to add new services that we haven't even conceived as of today. It has been designed for hosted payload from day one, and we have numerous potential candidates, including, of course, this big audience we have today. And unique architecture advantages that we have from current constellation will be carried over to the next constellation. So let's go a step deeper into the hosted payload. This is the original concept of 50 kilogram, which is of course still the concept. That's the total mass, volume, power, and the data rate allocated to this box. This volume is all we have allocated for the hosted payload. This is an opportunity to host third-party payloads, and it would share the infrastructure of the Iridium Next satellite and rest of the communication infrastructure, that is the crosslinks and the downlink and the gateway and so on. So you don't have to worry about any of that. You worry about the hosted payload, and we give you the data on an IP port, and that's really all there is to it. So you share the infrastructure, and therefore you share the cost, and give us the cost reimbursement for that. It's been flexible capacity designed into every next satellite. We have an ICD for this box, and then we have an ICD for the sensor part, which Chad will present after I finish. The ICD for this box and also for anything else that's inside of this box that we heard from Lars earlier today would be finalized by the PDR of satellite. So this is really the value proposition that we bring, unprecedented geospatial and temporal coverage, 66 interconnected satellites with coverage over the entire globe. There's nothing like it. Low latency because of the crosslinks. The data from your sensor in the space from any of the 66 satellites is presented to your laptop via IP connection within a matter of seconds. It's a real-time data access to your sensor. And it's a bidirectional, so you can not only receive the data, but you can also command the sensor and send it some software upgrades if that's what you want to do. Data collection and payload access through Iridium infrastructure. It's cost effective because you're really not launching satellites, which Lars had adequately illustrated. You're sharing the cost, and because it's a 50 kilogram total, it's proportionately much less compared to our total satellite constellation cost. It's exclusive. You don't have anything else in the horizon like this for next several years. And of course, it's consistent with the national space policy that Lars had shown in the chart. So I'm not going to spend too much time here. You've heard a lot from Lars, and Chad will basically expand this chart further to you. Just to say at the top level, this was really conceived as a way to utilize the unused mass, volume, and power from a larger hosted payload. Because we started with 50 kilogram, and we kind of realized that many of the projects that we are considering and are a serious candidate don't really use the full swap. So it leaves an empty room for us to really make use of other programs such as this sensor pod, which then led to GEOScan. So here's the conceptual view. So here, this is really 50% being taken by the shared hosted payload. This could be 60 or 70 or up to 80. It still doesn't matter. We have basically taken the rest of the space and compartmentalized it into 20 by 20 by 14 cubes, which is a single sensor pod. So, and then to mitigate all that, to manage all that, there's the things hiding behind here, which you'll hear more about from Chad, is the hub. And hub will basically distribute the power, bring the data from all the individual hosted payloads into the spacecraft and into the ground. So the volume can range from 1U all the way up to 2020 by 14. Package is a standardized sensor pod, which is again very important, like we talked about, and that's what makes this whole thing possible, is standardization, alongside another shared hosted payload. We, of course, provide you 3-axis stabilized platform, power, data communication, entire volume and mass. So you're really worrying about the payload. You're not worrying about building a CubeSat or a satellite, where you have to build all those subsystems. So that really is a great power of our capability, is all 4 to 5 kilograms that you have is available for your mission. The architecture does allow for hosting multiple sensor pods on a single SV, as you can see here. As a minimum, of course, we are looking at a single one across all satellites, all 66 satellites, and putting in one box like this and a hub and rest of the payload. It would enjoy all the, a hub would provide the interface, and a specification is available, and Chad will go over that. Sensor pod really enjoys all the benefits of a constellation, such as real-time data, without requiring ground station global coverage, while enabling a long mission life, because our satellites are designed for 10 and mission life of 15. So you can design a sensor for 10 to 15 years. You can really get all the data for all those years, at low cost. So these are the top-level specifications which you have seen already. A little bit about how the data is going to be brought down to the ground to you. Satellites basically sense the Earth's atmosphere or whatever you're interested in from scientific perspective, and then through our crosslink constellation, data is downlinked along with the rest of the traffic. Our customer traffic is downlinked to the gateway, and we have several teleports that are are part of our network, so it can come to any one of them. And from there, within our facility, there's an interface to Earth observation center of some sort, and through the IP socket, you get the data to your computer on the ground. And then you own this data and basically do whatever you have to do with it to calibrate it, process it, and create more value and do scientific analysis with it. And then it's available to end users all over the world. Here's the top-level schedule. You saw a version earlier, but it's basically the same schedule. Thales Alenia Space is doing the satellite PDR and CDRs over here, and we are roughly here, actually. This moved up a little bit, so predated a little bit. And then the last opportunity for a non-conforming is December of 2011, basically this year. And last opportunity for first launch is for conforming payload is over here. So I'm going to give you a quick view of what we have considered as potential projects for 50-kilogram class primarily, just to give you an idea about what we have already been talking about in the past 2 or 3 years. So we did 6 feasibility studies for NOAA between 2008 and 2009, all completed, data submitted to NOAA. This includes GPS radio occultation, solar radiance, sea surface topology, Earth radiation budget, ocean color, and ozone profile. And you can see some of the study partners that we had. And all these results are available. Many of, in fact, all of them were shown to be a good fit for the 50-kilogram class payload. And I'll show you a couple of examples. Space weather is another one that is easily doable from a GPS radio occultation sensor. scientific experiments using sensor pod, which is what we are talking about today. And then we have other projects such as ADS-B for monitoring the aircraft from space and providing their position information, maritime AIS, forest fire observation, and so on, and other DoD projects, space situational awareness, and so on. So there are many, many projects that we have considered. A few of them obviously have become our prime candidates, and as I mentioned to you, many of them don't occupy the full space, so we have sensor pod program available to fill up the rest of the space. So here's the example of the GPS radio occultation. This one shows 12 GPS receivers hosted on Iridium Next that can give you up to 14,000 high-quality occultation measurements per day with 12 sensors. And you can see the dispersion of all the data all over the globe. And it's pretty dense, actually, and it gives you all the information that you're looking for. We've done some preliminary analysis on the RF interference between Iridium L-band and GPS L1 band, and it was demonstrated to be manageable, but more work needs to be done in this area for any kind of GPS mission that we carry. And side benefit is the electron content of ionosphere and density profiles, and that's also possible. This is the second example of broadband radiometers that we studied with a UK-based company called SEA Limited, and they have done the GERB experiment. And they came up with an experiment with the instrument that was 23 kilogram, 39 watts power, etc., and volume of, so all the specs you can see over here. Just to give you an example, this really does very well compared to alternatives such as Clario, and it's quite complementary to the data you would get from that. Here's another example of optical mission using the METIS camera, and with the 9 of these, you can get a revisit time of 4 days. You can see this area being mapped, and there's a time running here. You can see this completely covered in 4 days. So, and this was studied for NOAA, and you can see how this will work. So I would summarize now by saying that Iridium is a unique and time-tested and operationally proven system. It's been there around for 10 years and growing successfully. It is our next generation satellite constellation development is underway and would provide business continuity and enable new MSS mobile satellite services. It gives you a unique opportunity and a capability to host payloads, significantly enhance Earth observation and remote sensing. Hosting of sensor pods is a unique opportunity to deploy CubeSat class payloads, 1 kilogram to 4 or 5 kilograms, into LEO orbit without requiring a development of a full satellite, and same benefits that our larger payloads will enjoy, such as real-time data, global coverage, no ground station, long mission life. It's really a new paradigm. It's a revolutionary approach, and GEOScan stands to take advantage of that. And we are very excited to know that the energy and the enthusiasm that Lars has exhibited can be possibly implemented in the next 2 or 3 years. Time is running short, and we are looking forward to making this happen. Thanks very much. Okay, so we have interface control document for the 50 kilogram payload, 50 kilogram, 30, 40, 70, nadir viewing, and so on. So if there is a hosted payload that completely fits inside that specification, that's a conforming payload. That's for the 50 kilogram class. For sensor pod, it is 20 by 20 by 14 and 4 to 5 kilograms because of the hub, there's a little bit of variation of between 4 and 5. The power of 5 watts average and so on. So there are detailed specifications. Both documents are available. If your hosted payload fits, it's conformal in any regards. And there's other things such as other parameters also that you need to worry about. If it fits exactly, it's conformal. You have until the CDR. If it does not fit, it requires us to do some extra engineering analysis, work with Thales to make them aware that this could be a potential hosted payload, get their buy-in to make sure that they accept that this kind of payload would be accommodated. Of course, NRE is involved with that. That is non-conformal, and that has to be done by the PDR.
Further questions?
Yeah, so if a payload required some sort of antenna or other feature that was on the RAM surface, that would be a non-conforming payload that
Exactly.
does not fit into the small box.
That is correct. I mean, if you go outside the box, the 30 by 40 by 70 or 20 by 20 by 14, then it's non-conformal. That's correct. And that would require a study of some sort,
Right.
sort of a.
So then I would imagine that some of the payloads that are being discussed here for GEOScan would probably be non-conforming payloads.
Well, that's to be seen, I guess. We'll have to take that on a case-by-case basis, see if, even though they are not conforming, whether we can do a study to retire that risk and be sure that we can actually carry it. If we can't carry it, we got to know.
Thank you.
I think fortunately for at least GPS, that's been the one thing that we're presuming would be a possibility. So that there's been more thought and analysis gone into what GPS interferes,
yeah.
things like that. So.
I have a question about the ephemeris information. You say that the satellite's going to provide ephemeris information for the payloads, but that's pointing. Do you have anything of a way of getting at more precise pointing knowledge for a down-looking imager or something like that? Because you need to know that. Is there a possibility of putting a star tracker or something on the spacecraft on the top deck of the spacecraft?
Right. The plan is to put the star trackers on our satellite. There's a group of them already being planned as a part of our satellite. There is a plan for providing a fixed telemetry information from the satellite through using the same space-wide interface into the hosted payload, which would most likely consist of ephemeris, possibly some attitude data. That part of the interface is still draft. It's available. We can provide you with that.
Okay. So just to be clear, you're planning to put star trackers on the spacecraft, provide star trackers and pointing information, pointing knowledge to the payloads that are on the nadir deck. Is that correct?
To the payload that is hosted on our satellite.
Right.
Through the
Right.
space-wide interface.
Right.
Yeah.
Okay.
I'm going to interject two things. One, don't forget to state your name and institution. Two, I think you're planning to provide pretty outstanding attitude, knowledge, and precision.
Yeah, we are still waiting for the final analysis from Thales. Once we have it, we should be able to make it part of the spec.
Yeah, well, pointing knowledge is key. Thanks.
Yeah. Now, with the star trackers, they're in the process of updating the spec. You will see the spec coming up in chat presentation, and that's at a course level, and then we're certainly aiming to improve that with the star tracker.
Okay, FT is Esther from Air Force Research Lab. If I understand you correctly and the presentation here before, there is overlap between the hosted pod and the hosted payload. And if I understand your figure correctly, the RAM real estate available for both combined is 20 by 20 by 20.
No.
That's the total available RAM, is that correct?
The total available RAM for any total payload, let me just bring up that picture. You can see that this is the total 30 by 40 by 70 box.
Oh, that's the RAM direction.
Yeah. And the RAM direction is, this over here, which is
over where?
40 by 70 total. So the RAM for the sensor part is 20 by 20. This 14 is the height.
The RAM is to the right, not.
Oh, I'm sorry.
So it's 20 by 20.
No, the nadir is.
As I said.
Yeah.
Nadir's this way.
The nadir is
RAM's up that way.
40 by 70. The RAM is over here.
20 by 20.
20 by 14.
Times 4.
We can, you can see that this is the RAM here, right? This one here. There. And if you look at this surface here, this is 20 by 14.
Oh, it's 20 by 14 each cube.
Yeah.
Yes.
Okay.
I think Chad will probably cover that in greater detail.
All right. Thank you.
Any last questions before we move on?
Steve Jaskalik, APL. Just to make it clear, you studied, I think it was 6 prospective payloads that you might fly in this, all of which were fairly large, power-intensive payloads. None of them are being considered for GEOScan. That's correct?
That is correct, yes. GEOScan is really all about the small payloads.
Right.
Those are all big payloads.
And so
they could complementarily exist. And
you were just giving an example of how you can do good science from this platform, but not in this particular program that we're talking about today.
That is correct.
I think our job is to try to identify and capture some of that science, but in a smaller, less power, less volume. If we can do some of those science, well, we can get them on all of them. We can do that. All right, should we give one more round of applause and continue on?
Thank you.
All right, next up we have Chad Fish, who's going to discuss in more detail the sensor pod concept and some of the possible science. Chad, which one are you?
GEOScan sensor pod.
This is laser and so is that.
So Lars and Ohm have given the motivation, the compelling story, and the value for using SensorPod on Iridium NEXT to implement GEOScan. And it really is a great opportunity if you think about all the work that's gone in the picosat, CubeSat, nanosat community over the last few decades. Here's an opportunity to take those sensor developments, that technology development, and now simply put it on Iridium NEXT and let Iridium NEXT implement the constellation for it. It really makes it easy to think of doing this global science, because basically the load of coming up with a spacecraft, coming up with a way to get to space is taken off of you. And that's been talked about this morning, and that really is an important feature of this. And by doing that, you can then just focus on your science, you can focus on your sensors, and you can benefit from the real-time data. And this is a very important thing. You can benefit from this global coverage, real-time data that you get from Iridium NEXT 24/7. Go out to your laptop, get on the internet, and basically through a simple internet protocol, bring your data down, and you're hooked in to this global coverage. It really is something that we should take advantage of. I'm excited to participate with this group. It's really been a pleasure to be a part of this, and looking forward to this going forward. So today I'm going to take a few minutes to walk through basically the information that's contained in the SensorPod ICD. And that was put together roughly a year ago, not quite. Last summer we distributed it, and it's out there in public domain. The easiest place to go get a copy of that is probably from Iridium's internet site. So this is a general listing of the baseline resource allocations that one will work with on the SensorPod for GEOScan. And as Ohm described a minute ago, those systems that are put together that conform to this allocation of resources and these interfaces are those that will be conformal. As Ohm was describing, you basically take the SensorPod building blocks, and there's multiples of those that can fit into one hosted payload, secondary payload area, and you basically put them down in that area and make the best use of those resources. Just to emphasize, the RAM direction is basically, it's a little bit difficult to see here, but in the plane, looking up and to the right, and the nadir direction is down and out of the plane there. So you do see that you get a couple of sensor pods that can look in the RAM direction. There's many sensor pods that look in the nadir direction and off to the side a bit. Basically, the field of views that are allocated to each sensor pod group, it's a cone, and if you're looking in the RAM directions, you basically have a plus or minus 70 degree cone that you can look. And then if you're looking down nadir, you have a plus or minus 75 degree cone that you're looking into. And depending on how you set up your different systems and your different sensor pods there, you can take advantage of different configurations, obviously. These sensor pod building blocks are essentially notional allocations, conceptual allocations of different resources. It doesn't mean that each of those blocks is a solid structure. You really have to just work to the mass, the volume, the geometry, and the different power and data rates that are listed there. And if you stay within that, then you become conformal. Now, for the GEOScan sensor pod, the system set, we definitely want to focus on staying within that common, that baseline sensor pod allocation. However, I suspect that as we get into the different hosted ones, there is the ability to consider maybe a 2-sensor pod. Indeed, these sensor pods are scalable. As Ohm mentioned, though, one has to sit down and work with Iridium on the impacts and how that interfaces with the rest of the spacecraft. But that capability exists to basically scale a sensor pod building block and use more or less of the resources. Just to go through and make sure everyone's comfortable with the different resources that are allocated for a sensor pod. 4 to 5 kilograms for the total mass. Volume's 20 by 20 by 14 centimeters. The power is 5 watts average, although there's an allocation also for peak, basically turning on or other special operations that might occur. And that peak right now is defined as a 1% duty cycle. Talked about the field of view and basically your viewing options. Data rate, 10 kilobits per second average. But once again, there is a peak that's defined as 1% at 100 kilobits. Another amazing thing that you get from working with Iridium is that that data is going to be basically coming down all the time. You can have high confidence in getting it. There's essentially a 97.8% availability rate that's been established on this previous Iridium set. The pointing accuracy, there's roughly a half-degree peak error in the pointing accuracy. Once again, these are peaks, maxes. These are not 1 sigma numbers. And then there is a knowledge that's going to be provided of roughly 0.05 degrees. Now, those are a little bit in flux. As Ohm mentioned, they're working the star camera implementation on the spacecraft and where it's going to be located. So those numbers might change just a bit. As you put your sensor pods together and interface with the spacecraft, there are thermal conditions that are maintained basically on the spacecraft deck. And the values are listed there. For operational, the spacecraft deck will be maintained between minus 20 and 40 degrees C. And then the survival is minus 40 to 60 degrees C. So our systems have to be developed to work within that environment. That's just a spacecraft deck. Obviously, we'll have to understand the full thermal design of the GEOScan sensor pod to understand how the thermal system is distributed. There is a limit on how much of the heat generated in the sensor pod that you can give back to the spacecraft. And right now that's defined as 30%, so roughly about 1.5 watts for every sensor pod. The rest of that has to be radiated to space. So that's another limitation that one has to consider as we put together these systems of instruments. Now, Ohm also discussed the need, the desire to stay within the sensor pod allocation volume when it comes to different types of mechanisms or deployables. However, we realize once again that those are possibilities, and many systems have those components as part of their inherent design. So those will be reviewed on a case-by-case basis. Doesn't mean they're out, but as Ohm was mentioning, the simpler the system and the easier it conforms to the sensor pod, the easier it is to go forward. Now, there is a thing called a sensor hub that accommodates or complements or is interfaced with the sensor hub, or excuse me, the sensor pod itself. And its job is basically to provide a bridge between the spacecraft and the sensor pod instrument suite. It's mainly an electrical bridge in the sense that it provides power that's conditioned, and it also interfaces the telemetry stream, basically puts the commands through to the sensor pod instrument suite, as well as receiving the telemetry from the sensor pod sensor suite, formats it, and sends it on to the spacecraft. By doing this, as one can imagine, we can offload a lot of the work and the burden that the spacecraft normally have to do and really lessen the impact on the spacecraft. The sensor hub is a modular avionics design, and we can actually stack pieces together and interface with multiple instruments in a sensor pod. Here is shown a number. We're not expecting to have that kind of interface on the GEOScan sensor pod, but that capability exists. So So it's a very modular system that can expand out and address basically all of the payloads, whether they're sensor pods or larger size payloads in the hosted payload section. One thing that's also going to be very important is, and it was discussed a bit earlier, the sensor hub itself will be able to interface with the spacecraft, acquire housekeeping, other metadata, other operational data that's important, say, to a certain sensor in a sensor pod, and it can transmit that data on in a formatted way. It can also inject that same information into the actual full-up telemetry stream coming out from the sensor pod as it goes down to the ground. So it provides a very nice interface between the spacecraft and the sensor pod. Just a few more of the details as we zoom in on the sensor hub guts. Basically, it's going to provide different voltages that are conditioned, and those are switchable on and off, and they can be commanded. In addition to basically just providing that switchable operation, the sensor hub will also have smarts in it to look for overcurrent and other conditions that are not desired on the power system, and it can shut things off temporarily or permanently. There is also a soft start circuit involved in the power up to provide basically a gentle power up for the sensor pod systems. There are a number of different interfaces that can be used between the sensor hub and sensor pod as far as transmitting data. RS-232, RS-422, and SpaceWire are the baseline interfaces that are established right now. Now, as part of the sensor pod ICD, there is a discussion on testing and verifying a sensor pod before it is delivered to a spacecraft. So the sensor pod will be assembled and it will go through a test suite to ensure that it meets the allocation of the resources as well as the interfaces that are established to interface smoothly with the spacecraft. Now this will include basically mass, power, and data testing to make sure that those are not exceeded. There will also be environmental testing that will include vibration testing, thermal vac testing, and possibly EMI and radiation testing, but that may also be able to take care of through analysis. As we're doing a large number of instrument systems, there was a discussion earlier about how Iridium was somewhat novel in putting together that first constellation. They were very hands-on and basically producing a batch set of satellites that could go up, and as each version was built, it got cheaper and cheaper. There might be some kind of processing like that that we can approach on this GEOScan sensor pod, basically through qualification acceptance or some kind of batch or tag testing to limit the number of test sets we have to go through on each of the sensor pods. So in summary, there's established ICD baselines that are accessible to the community, and because of that, we have a clean way to interface with the spacecraft. A lot of the burden's taken off of us already to come up with those interfaces. So at this point, we can really just focus on developing the sensors, making them fit into and conform to the established sensor pod, and then moving forward with that, focusing on the science and the performance of the instruments, and then take advantage of the high data rate as well as the real-time access to data that we can get from Iridium on a constellation that's established by them. Thank you.
All right, thank you, Chad. We got questions?
Tommy and JPL, you mentioned the attitude pointing knowledge, but I didn't hear anything about the ephemeris accuracy or precision. How good's the OD that we expect to come off of this?
That I don't know. Ohm, would you happen to know the information on that? Sounds like when you take that as a question, we'll get that offline for you.
Dave Klumpauer, Montana State University. Just a couple of clarifying questions. So I understand the concept within the hosted payload volume, there are multiple allocations. That is to say, there's allocation for multiple sensor pods in some sort of a jigsaw, 3D jigsaw fashion. Correct?
Correct. That's a potential way of putting it together, yes.
Okay. And then to further clarify, with respect to the sensor hub, is it the vision that there's a modular, expandable sensor hub that handles as many of those a single one that handles as many of those sensor pods as are manifested on on the vehicle?
So that's a good question. Right now, there's an opportunity for one sensor hub to be integrated directly with the sensor pod. It could be some type of backplane system, or it could sit off on a box. The sensor hub itself, the way it's designed, it can interface with multiple sensor pods or payloads at one time, up to tens of payloads if necessary. So there really will probably be just one sensor hub that addresses all of the sensor needs. That's the intent.
Larry Paxton, APL. I just had a quick question about jitter spec. Do you have one for the payload?
I don't have the top of my mind. I know that you've mentioned that to me, Om. It is. We can dig that up for you. I didn't put it in there. It's a good point.
Further questions, Ken?
Hi, Tom Woods with the University of Colorado. Question on the sensor hub, is that integrated part of the sensor pod, or is that an external part of that?
So nominally, it's external. However, there's no reason when we have such a large number of things coming together, such as the GEOScan sensor pod systems, that we couldn't integrate it with them, if it makes sense. So there's a potential that it could be integrated right in with the GEOScan sensor pod.
And for another kind of related question is for hosted sensors, particularly where you might have your own sensor pod, or is there options for APL or SDL to provide a common, microprocessor, power distribution board? I mean, those are common things that all instruments need, and especially if you're red hard parts, you have to buy a large quantity.
Exactly, that's a very good point, and that's sort of the intent of the sensor hub itself, is to try and make a common system that all those can interface to. So I could envision on a number of the different spacecraft that you have the GEOScan sensor pod, and then there's maybe a hosted payload or two, and they all interface to the same sensor hub. It's got enough bandwidth to handle those kinds of things. Bits.
I think it's kind of obvious, but I presume these are non-articulated, right? And these are all passive, completely passive.
So once again, that goes back to the nominally, yes. But I think that Iridium and others are willing to consider any system, as long as it doesn't, one, become grossly nonconformal, and two, it doesn't interfere with the primary mission of the spacecraft. I mean, that's what's of greatest concern to them.
Another concern would be the spectrum is licensed, and that aspect has to be addressed.
So some kind of mechanism to move things around or deployables. Yeah, there's going to be some. So we, once again, we'll have to look at the impact it has on the spacecraft. I would never say don't do that because of that, because there's a lot of sensors that need that.
Yeah, I think the main thing to keep in mind is that Iridium is probably willing to consider almost anything, but if you're going to be non-conforming to potentially affecting their main business, well, then you're going to have to pay for the engineering analysis to make sure it's not going to affect my main business, and that's money. So if we want to do things as cheaply as possible, we want to stay away from that. But there's a strong motivation to have to do that. That can be identified, and we can identify how to pay for it, and I don't think we should exclude it.
Let me ask the obvious following. In that the things that would throw payloads out, there's a hierarchy of things that have become too difficult. And so articulation is one of those things where you're impacting the inertial system. That's a big deal to any satellite. So have you guys thought through how to throw things out fast?
I think as I briefly went over, if you envision that matrix with feasibility versus science impact, if it's a big pain in the butt, but it makes a tremendous science impact, then it's worthwhile perhaps shooting for. But on the surface, the easier, the bigger the science impact. If there's clear sensors that ought to fit right in that left corner, and that's what we ought to drill on, because we don't have a lot of time and a lot of money to do. But if it becomes really clear at the point, that would be great if we could do it. It requires two really great capital.
Jesper Gallo at APL here. Two brief questions. The Mac, I assume you're going to have an Attitude Mac, right? Are you going to run that in, is it an upgraded Mac in any way? Or how are you going to run it? Is it in the Ampere upgraded mode or the old mode? I mean, what are you going to do with the Mac? Is it more of a science Mac?
I think you're still discussing that, aren't you? Or has that been finalized?
Discussion, but I don't know how much I can comment on it. But we're planning an Ampere next, essentially. But it's not yet obvious. We're going to be able to use magnetometer data, but we're still working on the details of
Okay.
what that's going to look like.
Okay, and then the second question, very briefly. I might be the only one in here who still don't get it. According to this figure, right, there's 8 of these sensor pods. Okay? According to Lars's discussion there, one of those 8 was going to be chopped up into one of these system-wides, and then the remaining of one of those sensor pods, one of those 8 there, is going to be available for people. Is that part of GEOScan? Is that correctly understood?
So one of those will be the GEOScan sensor pod, yes.
Yeah, and
the rest of that is, we'll call it, just a kind of a conception as to what could happen. Obviously, it's heavily dependent upon the different payloads that Iridium Next is provided with, not related to this program, and how to fit all this together. But a hosted payload could then utilize some of the other leftover spaces, and maybe it's 2 of those blocks or 3 at the most, something like that.
Okay.
I wouldn't say that picture is just a place to start. I wouldn't say that actually grabs what we're going to do on GEOScan or any other thing. I think it's just sort of a conceptual way to think about putting things together.
Okay, I think I get it now.
Yeah, let me follow on Jesper's question. Clarification on the figure. You've identified the RAM and the nadir. I don't quite get where this fits way up in the cone. What is to the left and to the right? Is this a space that is basically inside a bigger enclosure part of the bus? Is it by itself? So to the sides of it, is there bus? Is there space? Yes, indeed.
So can probably comment better on that. There are things there, but go ahead, Right.
At a high level, this is a native where we have some hardware for the feeder links and the cross links. So you can see a little silvery object over there, that's the feeder link. And then an object on the right-hand side is the cross link. So those are antennas that we need for our own mission. So there's hardware on that deck. The bus and all the rest of the hardware is inside the...
But it's not like the whole side is occupied.
No, there's empty space in between.
No, so...
On the sides.
Yeah.
Well, I mean, you can see that the antenna obscures the view quite a bit. So if you're thinking about a mission that looks to the side, it may not be completely, good view. Depends on what you're trying to do. It also depends on, where it sits with respect to the rest of the hosted payload. Because as you know, our business model is we have a main payload, which would occupy 50, 60, 70, or 80% of the volume and the mass. And then there's a sensor part, which would occupy maybe 1 or maybe 2, and the sensor hub. So that's basically the concept here. So basically, if you got a main payload, which is 80% of the resources, then it's going to take up quite a bit of the available space, and so you're only limited to what's left over. So our view is that we would allocate the RAM facing, the forward facing, and the nadir for the sensor hub and sensor part, so you get the advantage of that. So now, if you put that towards the top end, you're going to get obstructed by the 2 antennas on either side. That's how it's going to play out. It depends on what else is on the satellite.
Yeah, so there's thermal considerations, or yeah. One thing that I ought to note too, and the spacecraft is still in design, so there's not a final word on this, but one should know that those, and you probably can see it, that those solar arrays are articulating. So there will be periods of orbital time when they're basically moved almost parallel to the spacecraft, and so up front they'll be off to the side.
Hey, Marcin Polinsky, University of Colorado. My question is related to alignment. So if you specify some alignment spec of your instrument to the sensor pod, the pod is aligned to the overall box, and then the box is aligned to the spacecraft. If you have specific needs, will the cost go up? Are you providing sort of an integration package? And it kind of runs into a bigger question of how does the whole handoff of the instrument and who and how is the instrument integrated to the pod, and so on.
So that's a very good question. And as part of the sensor pod IC, where you integrate with the spacecraft, where the payload provider would come in and perform that alignment. And there's certain numbers that we've discussed, and we're still working those, and we'll have to work those with Orbital, but that you have an opportunity to come in and basically work on the alignment, understand what it is that your sensor is going to be aligned to, and that knowledge that you'll get down to the ground. There's also a level of cleanliness that's going to be followed, obviously, in the development of the spacecraft, and if you need a higher level, there'll be considerations put into place to address that.
So something like a nitrogen purge?
Those kinds of things, yep, can be worked and discussed. Obviously, the easier it is to handle, the easier it is to do, but those are all considerations.
Hi, Bob Erlinson, APL. I wanted to give one, there's a little confusion of the term, so I wanted to see if I can help that out. So I'll walk up to the screen here. Okay, so GEOScan involves one sensor pod per spacecraft of this size. So one of these boxes, that's GEOScan. Okay, and in that GEOScan sensor pod, Lars talked about 2 or 3 system sensors and one U hosted sensor. In addition, in that sensor pod will be some, call it subsystem type things like power interfaces and some of the things on Chad's block diagram. So the terminology we're talking for the GEOScan activity is one of these boxes, 2 or 3 system sensors, one hosted sensor, one U-type thing, and then some of the infrastructure, power, conditioning, FPGAs perhaps, things like that. So that just clarifies that's what GEOScan is. If I could interject, Chad, if I'm correct, they were going beyond GEOScan in terms of a system that could host multiple boxes. Okay, but GEOScan is one of these boxes. So hopefully that clarifies what we're talking about.
Yeah, I think the main thing that we're trying to consider, GEOScan is a single box. The system sensors and the hosted sensors all fit inside one sensor pod box. Because the hosted sensors will be unique to each spacecraft, we want to ensure that, elongate our timeline as long as possible, to have a uniform ICD for GEOScan. So that way Orbital, the integrator, and the Iridium knows that whatever we deliver to you is going to conform to this spec. And that gives us the maximum amount of development timeline to fit within that spec. So there's a single interface to the GEOScan pod, and that won't change. And what gets delivered in terms of thermal and mass won't change. And so we'll have to do adjustments for the hosted sensor. But from the interface standpoint, it will be identical to every single thing that we deliver. That allows us to accommodate unique hosted sensors for the longest time development timeline possible.
Dave Klumpar, Montana State again. Just wanted to clarify a possible compatibility issue that it's obvious, so I'm sure people have talked about it. With the sensor pods very close to those crosslink antenna, that crosslink antenna array, which is presumably radiating, and let's just imagine a very sensitive receiver like a GPS system with an antenna fairly close to that. We've all thought about, I gather, the compatibility issues between, desensing a receiver, et cetera.
So it's been considered. I don't think there's been any real effort put into putting numbers together and levels that could interfere with one another. But it's a very good point. They're high frequency.
Or could there be sub-commutation time sharing between, say, science receiver?
Those crosslinks and feeder links are crosslinks and feeder links are to support our primary communication mission, so they will be utilized as needed. So there's no plan to share or anything like that. I mean, the analysis has to be done to make sure that there are no radiative effects from our hardware into the hosted payload and vice versa. That has to be done, and that's why anything that does not conform, that has to be studied. Even if it conforms, that has to be studied and made sure that there are no kinds of adverse effects on either, or the main mission or on the sensor.
All right, so I think I'd like to cut it off here because as important as these discussions are, coffee is also important. So we're well into our break time, so let's all take a break. We can continue these conversations informally over break, and I want to stay, we have a packed schedule, so I want to stay close. Everyone thanks, give that a round of applause.